So, as we are continuing on to part two, I wanted to do just a quick review of what we covered last week. Just make sure everyone's on board with what we have covered and what's kind of coming next. So, we had generated our chip layout using a number of components. You can see the final product on this right-hand side of the screen in the GUI and an image captured in the notebook there. It's a combination of transpond pockets, cross bonds, pathfinder routings, transmission lines, some capacitive couplers, and a wire bond launcher. So we decided what would be good initial options and parameters for setting our target quantum values that we were after, such as what kind of G did we want, what kind of readout chi did we want. Of course, these were just kind of educated guesses because to hit those specific values, you have to end up doing some kind of simulation and analysis to figure out what your layout is actually translating to. So once we had the buses with our estimated lengths, and finally all of the readout section, we were able to start getting to the simulation and analysis. So we started off doing the LOM on a single qubit. We first were just focusing on qubit 0 over on the left-hand side here. And we were able to run it through the LOM analysis, specifically focusing on a few of those key values, such as what the qubit anharmonicity was, what's the coupling to the bus resonators, and what the readout chi would end up being. So after doing our initial simulation, we saw that none of the values were what we were wanting. We wanted a chi of a megahertz. We wanted the G to be about 80 megahertz. So we needed to make some changes to our qubit. So we were able to go through, improve the convergence of our simulation to make sure that we're getting good results. And once there, make the necessary modifications to our layout so that we could get the actual simulation results to show that the modifications we made to the layout were allowing us to hit the quantum parameters that we were interested in, that you can see highlighted in yellow here. After that, we jumped to the looking at tuning a bus resonator. So we were doing it in a sort of first just rough approach. We were focusing on bus 02 over here. So we were doing that by just rendering in bus 02, qubit 0, and qubit 2, but just having those qubits as capacitive islands, not actually active junctions. So we did that by setting the ignored JJs to specify those junctions should not be present in the simulation. That allowed us to do a much faster simulation and get the initial estimates of what that resonant frequency is, specifically because if you were to just render that resonator on its own, you wouldn't be including the coupling portions at the ends of the resonator, and your resulting simulation wouldn't give you an accurate result. So from there, we were able to determine that, okay, our length's not quite right, but really this is a slow way to go about it. So why don't we instead see about setting up a sweep so that we could check a number of different potential lengths and see what's definitely the correct one. And if you recall early, sort of at the start of last week's tutorial, I mentioned this is still very much in development. Things are progressing and changing. We're getting feedback from the users, we're finding bugs, we're improving the code. And this is one good example because since last week, the sweep methods have actually been improved. So now you can include a greater variety of options for what you want the renderer to do with open pins and also how the junctions are treated. So the sweep, we can mimic how we did the previous simulation in that we tell the two junctions to not be rendered so that we're only simulating the eigenmode of the resonator, the qubits are still there for their coupling and their charge island aspect, but it allows for the simulation to be faster because it's not needing to mesh that sheet inductance and add a lot of extra memory requirements. So from that, we're able to relatively quickly get a pretty good sweep of a few potential lengths for that resonator. If you recall, we were trying to hit a frequency for this bus of about 5.8 gigahertz. And you see from these two, so that roughly we'd be needing about 9.6 millimeters. So we go ahead and we just change that value right there. Now, ideally, you'd want to, again, make that check, modify it to the length you think it should be, do that simulation and confirm your estimate is correct. But we can eyeball it for here. We're not actually going to fabricate this chip. We can kind of skate by with MacGyver methods for some of this tutorial. So moving now on to part 2. This section might feel slightly more jumpy because, as I had mentioned, we're not going to go through every single step of simulation and analysis and tuning for the whole chip because, one, we're not actually going to make this chip, and two, that would be very time consuming, and I think many of you would get bored of my voice if we went through that whole process. So what we will be doing is continuing to jump to specific examples that follow the design flow or a potential design flow and seeing how to make use of different tools or simulation or analysis in Metal or that's provided by Metal in order to get yourself through that part of the design flow. So first off, we were going to kind of jump into EPR specifically because we want to see about tuning the coupling between qubit 0 and qubit 1. If you remember, for these two qubits, we're actually don't have a bus resonator. We have just a direct coupling transmission line. So, you could consider it as a high frequency coupler bus resonator, or just really it's a charge island that's capacitively connecting the two. How one would best simulate that, you could do it through some impedance method, but EPR gives it a faster and simpler way because you're able to just simulate the two qubits and that bus and look at the resulting eigenmodes and how the different fields are participating, how the fields of the different modes are participating with different parts of the structure. So to do that, what we would first want to do just to try to have a slightly more accurate results to our simulation and analysis, we can make the same modifications we did last week to qubit 0 to qubit 1. We know for the most part, it's going to be pretty similar. To hit the anharmonicity, we know it's going to be about the same. They're only about 200 megahertz apart in frequency that we were aiming for in the design, which again, I'll mention, do not fabricate this chip. That would not be necessarily a great design, what we're actually doing right now, but it's good for learning purposes. So we'll make those changes. So you can see now that those connection pads are about similar. We've got similar on the readout there. And although it was just a small change, so not as noticeable, the gap between those charge islands has shifted so that the anharmonicity of these two will be about the same now. So first, as we have done previously, we're going to need to make an instance of a renderer, in this case, the HFSS renderer. And we're going to want to make sure we connect to ANSYS. Once we are connected, we can activate a design. And then we're going to want to add an eigenmode setup. So in this case, we know we're going to want to look at two modes because we are interested in 2 qubits and the bus won't have any relevant mode because it's going to be, if we were to simulate that eigenmode, it's going to be much, much higher and not really of significant interest in this case. we don't necessarily know how many passes it's going to take. So we can just kind of start with a bit of a guess. You'd practically, as we had done previously when we were looking at bus 02, you're going to want to look at the resulting convergence, see how confident you are in how the eigenmode is converging and settling, see if it maybe needs more passes to get a finer mesh. Then we'll just activate that setup. Now for EPR, although we are not going to do variations in this case, just for the sake of time, you can set up the design variables into the renderer that EPR is able to consider, and so can do when EPR does its analysis, is able to look at those variables and provide the analysis across all the variations of your simulation. So in this scenario, the design variables of interest would be the junction inductance and capacitance. Now we're just going to leave capacitance as 0 for this simulation. And for the junction inductances, we're just going to use the values we've already set in the respective qubits. And if you recall, based off of the LOM we did last week, qubit 0 we have as 14.9, qubit 1 we have as 13.9. You can see now for this design, we have those variables located in ANSYS. So we, as I mentioned, we're going to want to render bus 01, qubit 0, and qubit 1. So we'll get that rendering in. Now, the simulation, of course, would take quite a while. So we're going to skip that. As we get into farther in the design flow, your simulations will start to take longer and tend to require greater amounts of computational memory. When you're looking at qubit to qubit coupling, that's a lot more meshing. It's going to take more memory and time. As you start looking at the, say, readout chains, that's even more memory, that's even more computational time. So it's something you want to keep in mind, especially if you're, say, working off of a laptop, as well I currently am. You may need to make use of a workstation for more precise simulations, and just use your initial passes with your simpler computer as a rough estimate, and then fine tune later. So pretending that we did that simulation, and the simulation is now complete, we can check the convergences. So you can see the eigenmodes seem to have settled down reasonably well. It's I feel comfortable saying that that has converged for our purposes. Now you might notice as well, though, that these frequencies are a bit high compared to what we were getting when we did the LOM analysis. And you'll see later that that's okay. Really what is important is that we're seeing that the spacing is about 200 megahertz, which is what we were designing for, and will be of that separation is also very important when trying to look at stuff like the qubit to qubit coupling, as well as their frequency, of course. But so once we've settled on being comfortable with the convergence, we can jump to actually starting some EPR analysis. Excuse me. So we'll go ahead and just import PyPR in order to call it more easily and directly. Make an instance of the analysis class there. We will specify some of the junction information that has been used in this simulation. This is just important for the EPR analysis, so it knows what to look at when it's doing some of the field calculations. So for junction 1, we're telling it, okay, these variables are attached to what we're calling junction 1, as well as these shapes. Now, if we zoom in just quickly so you can have an idea, if you recall, when we're doing rendering into, say, an eigenmode simulation or even a driven simulation, the junctions get represented at times as a sheet inductance. So that sheet inductance has the name, JJ rect underscore LJ. It's a long name, but very easily identifiable and won't get mixed up with others. We also have a polyline that we can use as reference for, say, directing an internal port, or in this case, we will be using it in EPR for reference as a voltage line, or the voltage vector for doing your line integration or path integration. So we'll set that info, also specifying the volume, which is our dielectric, in this case just being called main, and in this case it's just silicon because we didn't make any changes to our chip options earlier on. We can then take a quick look at the field distributions. Oh, my apologies. Of course, it won't calculate anything because I didn't run the simulation. From those field distributions, you can though find things such as the amount of the electric field that's present in the substrate versus the vacuum or air around the chip. And it basically is making use of the ANSYS field calculator in order to extract any of this information that might be of interest. Now, of most interest is the actual EPR analysis. So this I've already done. So we have this data file that gets saved, which contains all of the analysis that's been done on that field calculator. Now from there, I can run the analysis on the variations, and say in our case, we just have the one variation. So from doing the final step of this analysis, we're able to get, say, the resulting mode frequencies, in this case, the numerical diagonalization. And you can see that when taking account for the quantum aspect of the circuitry, our qubits ground states end up being about, or the 0-1 transition frequencies end up being about what we were aiming for initially. We can also then see from the Kerr matrix what the anharmonicities for our qubit are. Well, for our two qubits, I should say, because this is referring to qubit 0, this is referring to qubit 1. You can see there, well, since the layouts are near identical, basically on point as we expected. And we can also see the off diagonals, which is telling us the coupling that we're getting between these two qubits, in this case about 760 kilohertz. Now, once we've gotten to this point, we can determine, all right, is that the coupling strength we're after? If not, then we need to go back, repeat what we've done previously in terms of changing the layout structure, making any modifications to, say, increase or decrease that coupling strength. We can run the simulations and analysis again and see what the resulting cross curve is. Now, for the much more deeper dive in terms of what's that all mean, I'm going to say we'll dive into that in much more detail for anyone unfamiliar with PyEPR analysis in a later tutorial, but I definitely would advise people checking out the paper, as that's a good spot to get started if unfamiliar with the process. And this notebook will be shared later once it's all wrapped up and finished. Oh, a question, is it possible to simulate each component individually? Well, yes, you can. You just might not get as accurate a result. So if you recall, for LOM analysis, we did simulate the qubit individually. We had to input into the LOM analysis what the, say, bus resonator frequencies were in order to extract their respective Gs and other values of interest. But to get the most accurate result, you'll want to have more than one component simulated at a time. I'll say for the absolutely most accurate result, you'd simulate the whole chip at one time, like in one go. That's insanity. It would take so long. Someone else will have made a quantum computer to do the simulation faster by the time you're done that simulation. So figuring out the smallest subsections you can simulate and still get reasonable results and parameters is part of the intuition and like practice you get as you work on these. In terms of, say, qubit to qubit coupling, what you see on the screen, that's practically the smallest simulation you'd really be able to get away with. You could do, say, LOM on the 2 qubits and then just the bus resonator, and you would get reasonable accuracy in your results. But you would want to, if it's something you're fabricating, you probably want to do like a sanity check simulation like this with EPR just to see, oh, what's the capacitance matrix I simulated initially not quite right, or something along those lines. So from there, finally, we would just disconnect to ANSYS to hopefully avoid that COM reference issue and continue on with the next step of the analysis. So we'll assume now that we're at a state where all the qubits have been tuned, all the buses are tuned, everything's spot on to what we were aiming for. Now, we then need to start thinking about the readout chains. So, in this case, in the north side, this transmission line, readout resonator, and that capacitive coupling. Now, we did already do a decent tuning for the Chi with the LOM analysis on this qubit down here. But we have no idea if our readout resonator is at the right frequency. We have no idea of what kind of capacitive coupling we have with our interdigitated capacitor at the top here. So how you could go about this is multiple ways. One potential option is, say, that you know what the capacitive value you want is for that interdigitated capacitor. In that scenario, we could, say, make an instance of a Q3D renderer, aim to then set up a Q3D simulation, specifically doing a Q3D sweep so that we get multiple capacitance matrices for different geometries of this interdigitated capacitor. So in this case, what I'm thinking of doing, and this is very similar to the sweep that we did for the bus 02 eigenmode, I'm going to render just this interdigitated capacitor. I'm going to sweep the finger length, so the length of these interdigitated fingers here. I'm going to just pick three guesses of what those lengths should be. I'm going to make sure that all three of its pins are open, because I want to make sure I'm getting the capacitance of both sides of the resulting capacitor, and I don't want any of it shorted to ground, because then the capacitance matrix won't mean anything. And then I can run that sweep and just, walk away, go get a tea or coffee or whatever, and get the resulting capacitance matrices for each of those sweeps. So in this case, we can see, we're wanting to have the capacitance between body 0 and body 1. And here we have the column for body 1. So we're looking at this value here.
Thomas, quick question. I don't know if you caught this one.
Go ahead.
Maybe you answered it, but I missed it. There was a question from folks about what the minimum spacing for two adjacent qubits is to avoid Fourier-ZZ coupling induced by direct capacitive coupling. That's a question from Rui Chen Zhao. By the way, guys, yeah, please do post questions in the chat, and we can kind of pause and answer those and make this, a lot more interactive than just a lecture you watch on YouTube. We can really answer and discuss here as well.
Yeah, so it's a good question. There's not a solid answer because it's going to be very dependent on so many parameters. Also, honestly, it ends up being a case of it's something you just need to simulate and check, because dependent on the layout structure of your qubit, like how broad is your electric fields from your charge islands distributing it across the dielectric and resulting ground. You'd really just need to check, okay, what, like, say in EPR, seeing, okay, what is if we were to consider, say, this simulation, you could do something where you simulate it or you render it, but without the bus. So you get rid of that bus and then check the EPR at that time. And that practically would be probably the best way to go about it. You could also just like have a rough idea of like, okay, just do a Q3D of the two isolated qubits without the bus and see what's your capacitive matrix look like as you shift that spacing. There's not really, yeah, I'm afraid there's not an answer of, oh, it's 30 micrometers. It's going to depend so much on so many parts of your design that it's really something you just have to simulate and analyze, I'm afraid. But good question. I wish I could give you a solid answer, because I wish I could have a solid answer and avoid lots of simulation checks for other designs as well. So jumping back to the capacitance sweep, we were looking at that interdigitated capacitor. And we can see that at these different finger lengths, we're getting different values of capacitance. This is in femtofarad, of course. So from this, we could see, all right, if we were wanting 7.5 femtofarads from this sweep, we'd be able to say, all right, finger length of about 22 micrometers would get us the capacitance we want. Now, in addition to that, that's just telling us the capacitive coupling. So of course, we would also want to do eigenmode simulation on the readout resonator, say rendering the capacitive coupler, the readout resonator, and qubit 0, in order to make sure that we have the readout resonator frequency set to what we want. So you'd basically have a capacitance sweep and then followed by an eigenmode sweep. Alternatively, what we could do is just set up a driven simulation, as we could consider looking at qubit 0. So we could throw an internal driven port in there instead of having our sheet inductance, say. We could put a port on those two launchers at the top there. And then we could just look at, say, S31 or S32, basically seeing when we send a signal through this transmission line, checking to see at what point the readout resonator frequency is showing up, and also looking at the bandwidth of that dip or spike if you're doing through or reflected, in order to see what kind of external quality factor we have on that readout resonator due to the coupling strength. So that's going to be, again, one potential way. There is others, but it gives us a manner to do kind of multiple tunings at the same time. So in that regard, we would set up an HFSS render. We would connect and add driven modal design. Now, since we are wanting to do a driven simulation, we'll add a driven modal setup. Again, we know what frequency we want the readout resonator to be at. We don't know if it is that frequency yet. So even doing an eigenmode first can be a good way to check, okay, what should I be simulating at? But we'll set it to the frequency we're aiming for anyways. In terms of passes and convergence, again, similar to what we did previously, we're kind of making educated guesses. And I'm going to set it to basis order of -1, meaning mixed order. This, in essence, if anyone's unfamiliar with how, say, HFSS does its finite element method simulations and meshing, it's a series of tetrahedrons, and it's generating its resulting numerical methods matrix for doing its computations on by picking vertices and surface points of each tetrahedron, and the degree or the number of those points on each tetrahedron is determined by the basis order. So it can be 0th order, 1st order, 2nd order, or mixed order. Mixed order, we're letting ANSYS determine, okay, for each tetrahedron, you choose. This can be a good balance between, say, computational memory requirement, as well as getting better kind of analysis and accuracy around items of interest, say where there's a very strong amount of field and it's changing very rapidly. So we'll add that in. We'll make sure it's activated. And now for the actual render, we have a lot of stuff we have to render. So I've broken this down into different lists here. So for the render, we're going to need to put the qubit, the readout resonator, that capacitor coupler, and the whole length of the transmission line, including the capacitive coupler for qubit 1's readout resonator, but we're not going to include the readout 1 resonator just to keep the simulation a bit simpler. You certainly could, so that you can, say, try tuning both at the same time, make sure that they're not like managing to couple to each other too strongly through the transmission line, things like that. But that just adds the computational time required. For the 2 ports for this driven simulation, I'm not including the wire bond launchers. Instead, I'm adding at the ends of the transmission line here, I'm going to define a 50 ohm impedance port on both ends, and I'm replacing the junction for qubit 0 with a 50 ohm port as well. So then with those all there, I'll do that rendering. I don't want any open pins. Any pins that are open and not already been defined with ports can just be left open or left shorted. And the necessary port and junction modifications. So that will go ahead and start rendering it into ANSYS. Once that render is complete, you could then add the sweep. In this case, we're wanting to do, say, between 6 and 8 gigahertz. Now we know when we made the initial resonators, we were using that guided wavelength calculator. And since it wasn't including the couplers, we know that the length is going to be higher than necessary. So the resulting frequency we'll see is definitely going to be lower than what we're aiming for. So we aimed for 6.8, so we know the frequency is going to be lower than that. You could even start at 5 gigahertz, but I might have ran these simulations earlier, so I was able to make sure that the resonant mode gets captured. So you can see here now that the resulting render is complete. We have the qubit, we have the readout resonator, and we have the transmission line, all nicely wire bonded so that we don't have any unexpected slot line modes in the simulation. So we'll add that sweep in as well. And we've also specified it to be an interpolating sweep just because we don't want to be spending too much time on an initial sweep. We then run that simulation. So when it's driven, you're wanting to specify both the analysis setup and the specific sweep you're wanting to run for that analysis. Once that's complete, we can then go ahead and say plot the parameters of interest. So in this scenario, we see this 2 to 3. So we're seeing the signal from here to here. And we're seeing that big resonant dip. And we're even seeing that slight like S phase shift thanks to the resonator here. So our resonator is much too low a frequency. So we would want to shorten this length quite a bit to get it up to the range we were considering. And then for the actual coupling strength or the external quality factor, you could use the resulting this sweep and extract what's, say, even just doing the simple 3 dB check on a resonator to see, okay, what's my quality factor on this resonator? Now, since we're doing only right now perfect conductors, any part of the quality factor you measure is going to be the external quality factor. So you can be confident as to using this as a manner to extract the external quality factor. You don't have any internal quality factor component that is influencing that result. That within reason, because we do have that lumped port down there, but that's very weakly coupled compared to that full path there. So once you have that result, you can do the usual process that we've done previously, make the modifications, you'll rerun the simulation, check it to see it's like, okay, is it on frequency? Is that quality factor looking more about what I was aiming for? And once you're finally happy with that result, you can go ahead and make those changes and then finally disconnect that simulation. Now, assuming we've finally gone to the end of all this simulation, analysis, and tuning, and we're set that it's like, all right, design's good. We want to fabricate it. We want to get it into our fridge and start doing experiments on it. You need the resulting design in a format that's compatible with fabrication processes. So in that case, we want to be generating a GDS file. So to do that, we want to make an instance of the GDS renderer. Even if for an export, we refer to them as renderers because they are generally still series of like Python classes or methods or API commands to actually make that connection from Metal to some external software or external file type. So when doing that, we'll make that instance and we can see all the options. Some of the options of most importance, I'll say, is the path file name. I don't know if you recall from last week when making the qubits, I pointed out that we give a cell name that represents our junctions for when we make our GDS file. This path file name is the actual GDS file that's holding those what's the word I'm looking for? That's actually holding the respective e-beam layouts for your Josephson junctions. I hope that came across clearly, but maybe it's better if I explain again. So in essence, the Josephson junction in metal is the most variable representation component in all the design. In HFSS, it could be, or when you're rendering a simulation, say for a capacitance matrix like Q3D, it doesn't get rendered at all. If it's for an eigenmode simulation, it will be as a sheet inductance. If it's as, say, a driven modal simulation, it could be a sheet inductance. It could be as a combination of sheet inductance and internal port. So in essence, it will modify the most out of any other component to match what's necessary for the simulation, but also for actual fabrication purposes, you want the real e-beam layout. So a quick example, this is that fake junction.gds file. And you see here, again, emphasis on the fake junction, but you see a series of cell names of just different random sketches. And these get referenced for the component to know, all right, this is the junction e-beam layout I need for my GDS file. So this file is pointed to. We know from the previously what those components have in their junction file name or cell name, but we can still take a quick look here. And we see it right there, fake junction 01. So we know then that this e-beam layout, when the GDS is rendered, this layout will be inserted where the junction is indicated, rotated and translated so that's at the appropriate location. If this cell is too short, say that the gap here is just too large, and that's determined based off of the size of the junction that's drawn by the component code, additional lithography gets added to make sure that there is overlap with your e-beam layer here and your lithography layer here. The other recently added component to the GDS options that's interesting is cheesing. So anyone unfamiliar, it's just referring to vortex pinning sites. And it's a common practice, say, to add that to your ground plane as a way to try to mitigate flux noise and help avoid any vortex noise from vortices traveling around and such. So you can specify some options for your cheesing, such as the shape type, what's the size of them, what's the resulting grid size, as well as around your components, you can specify a buffer region that should have no cheese present. So we're going to make some slight modifications of these just to meet, well, what I randomly decided I wanted them to be. And then just go ahead and make that GDS. Now, here, oh, I just need to pull up the file now quickly. Now, the format of that GDS, wait, that's weird. There we go. There we go. Brilliant. So currently, the output of the GDS includes extra information It has the different types of Q geometries on separate layer ID numbers. Basically, for the time being, just giving you as much extra information, but all separable, so you can just grab the aspect that you're most interested in. You can see here that like on 199, that keep out buffer regions present. We can see, let me get rid of these, go through them. We can have the isolated ground plane. We have just the polys, the paths, the actual cheesing shapes here, and then the actual final GDS, which includes that cheesing. And as I was mentioning, you can see the respective, in this case, fake junction E-beams present where we were expecting them to be. Finally, at that point, you're done. Well, no, you're really just begun, because now you have to actually get it fabricated and like made and then put in your fridge and run the calibration and do all your experiments. But you've gone through an important and previously much longer process step for getting your quantum experiments started. You could see that what would have taken me and many others in grad school years ago weeks, if not months, can take on the order of a few days. Even shorter if you have a really good system for simulations. So it's, although still in progress, still in development, still buggy, it is still able to give a much faster turnaround time with respect to designing new and experimental quantum chips and getting those from your drawing board to your clean room and fabricated in a fraction of the time previously. So with that, as we're almost at the end of the hour as well, I think I'll just say thanks for your attention. And if there are any further questions, happy to take them. So keep in mind as well, if you're not able to stick around for any extra questions, next week is planned to be a kind of open Q&A session, so that you can save your questions for that week if you want some time to look over the notebook yourself, which we will be making available in the next day or two. Just want to, fix the typos and make sure everything's running smoothly all the way through. But yeah, glad everyone was able to make it.
Thomas, there was one question much earlier in the talk. It was how can we add inductance and capacitance as lump parameters, something like 0-pi qubit?
Oh, so if that question might have been answered while I was going through the EPR analysis, showing how you can have the, you can specify LJ and CJ. If it's with respect to, say, adding a non-junction base, like just you're wanting some other location of sheet inductance or sheet capacitance defined, we do not have any components doing that, but that's not inherently a problem. You could realistically just make a component, make use of the junction Q geometry, since that is what's made into sheet inductances currently. But for 0-pi, I don't see any inherent issue that you couldn't just make up that component with the current structure. I think I won't say it's 100% for sure, but I feel you probably would be able to.
There were other questions here. I'm trying to find the one unanswered. That the how to differentiate coupling induced by different paths. I think you answered that one, but just making sure.
Sorry, could you say that again? I didn't fully catch it.
How to differentiate coupling induced by different paths. For example, coupler or direct capacitance.
Oh, right. Yeah, so like in terms of differentiating, say if you just do the simulation and you see, oh, there's this coupling from this qubit to that qubit, but you're trying to figure out what's that coupling going through or what's causing that coupling, that gets trickier. I would say you probably would need to just look at the field distributions, maybe render subsections of your setup and just look at how's the results changing when you say remove one component. That'd be my suggestion at least. Oh yes, the previous tutorials are available on YouTube. At least the first one. I think the second one is also available on YouTube now, if I'm correct, Marco.
Yeah, yes, I posted the second one on Friday. Yeah.
Okay, yeah, and the links to those can be found in the Slack channel.
Thomas, there's another question. I don't know if somebody's answering it right now, but it's how are the JJ considered in ANSYS?
Just answered that, Preeti.
Oh, I'm sorry.
Oh, yeah.
Thank you, Dennis.
So there is another question that was not answered, I think. Can you please give background information about the ambient environment condition like temperature, mechanical stress, etc.? It's a little longer. Did you address this stuff during the call? I probably don't.
No, I'm about the ambient normalized to a certain temperature, sacred parameters. Oh, so yeah, so that I would say largely that will be what's a good way to so in these simulations, no, we're not accounting for temperature or mechanical stress or environmental conditions. If that is something you're wanting to do, then some simulation software is able to support that, but I would say a lot of the experimental setup tends to be focused around getting parameters to very specific conditions. So like having a very known temperature. As mentioned in a couple of the papers that I showed the links to during the talk, even those specify that, say, your permittivity of silicon will change at cold temperatures. So when you're doing your simulations, you'll want to consider that. So you basically do want to keep in mind what kind of temperature effects there could be for your simulation, but outside of that, it gets it does get a bit tricky. There's probably ways to do some of that, and I shouldn't say there definitely is ways to do that some of that sweep to see how it influences your circuitry. I would say COMSOL's probably your best bet for that. But and I want to say pretty confidently that there's at least been some experiments and or theoretical simulations on all that already. Should the superconductivity be taken into account in the same way then? Yeah, so that again, if you're referring to superconductivity, say as the kinetic inductance or how let's say, like, are you suffering current crowding at a sharp corner due to the supercurrent or things like that? That starts to, again, get kind of beyond most simulators' capabilities. Some simulation software you can modify or make tweaks so it's sort of accounting for the kinetic inductance. But that is also going to be dependent on your circuitry itself and your superconducting material and the sizes of your components. If you need, like, how much is your kinetic inductance actually having a role in your circuit performance? So, if your transmission lines are big enough, your kinetic inductance is adding like 1% effect to your transmission line inductance. So at that point, it's kind of like, well, it's probably okay. We can just pretend it's not there. But if it's suddenly like half of your circuit's inductance, then yeah, that becomes a lot more important.
Thomas, there's a question in the chat about whether the Josephson junction is considered as a linear element.
Oh, you mean
axis?
So if you're referring to like when we do it, like having the sheet inductance representation, yeah. I don't know of any classical EM software that would accurately simulate it as a non-linear. I might be putting words into my mouth because maybe COMSOL could do it, but most of the quantum analysis parts are basically taking the linear aspect of the EM simulation and determining the nonlinear aspects from that. So I definitely suggest, say, the couple relevant papers like the EPR paper or the recent LOM paper, and that gets discussed and explained a bit in greater detail.
And we'll do like in-depth tutorials on the energy participation and the lumped analysis method as well.
Yeah. And by we, Zlatko means he'll do the EPR because I still don't fully have my head wrapped around that. I get it well enough to use it, but for teaching it, I wouldn't trust myself.
Yeah, that's what 99% of people need.
Excuse me.
Go ahead.
Righto. Well, I guess everyone's kind of information overload, but as I said, next week we will be having the kind of open Q&A session. You can ask any questions, give any feedback, show off any work you've been doing in Metal, and say if you've ran into a wall or have an error or something pop up and you're wanting a more direct live feedback on that instead of just asking the question in Slack. Feel free to come to the session next week and we'll be happy to answer any other questions. But yeah, I think for now, I think I'll wish everyone a further good morning, good afternoon, or good evening, and thank everyone for coming.